Now we're going to look at the step response of the series RLC circuit, the series circuit, and then we'll look at the parallel circuit. So the step response means that we are going to apply a step to the circuit, which means basically that at some time t we apply this voltage. So at some time here it's t equals 0, this voltage is applied, and or the switch is closed and the voltage is now in the circuit. Sometimes this is also called the forcing function, but the forcing function here doesn't necessarily have to be a step. In this case, in this chapter, we're studying its response to a step. In later chapters, we'll study the response of a circuit to an impulse, which is a very short pulse, and maybe we'll also study the response of the circuit to a sinusoidal or an exponential input. So those are all different cases of what function is being forced onto this circuit. But in this case, in this chapter, we're going to do a step response. So a DC voltage will turn on when the switch is closed. So this was the differential equation that described the circuit in the absence of any sources. But now we have a source right here, and from Kirchhoff's voltage law, the sum of the voltages around the loop equals 0. So we see that the voltages across each one of the elements must equal the voltage at the source that's being applied. And we somewhat learned earlier in the first order responses, well, we did learn already earlier in the first order circuits, that the total response, the total solution to the differential equation is the transient response plus the steady state response. So the transient is the part that, in our case, decays with time. It's not necessarily that it decays with time, but this circuit, in the absence of any source, will decay with time. And then the steady state solution is what the voltage is at infinity. So after all of the transient, intermittent, short-lived behavior goes away, then we have the steady state response. And in this case, so V at infinity is going to be the voltage across this capacitor. And at infinity time, this capacitor is fully charged up and equals the voltage of the source, and no current is flowing. So we get the steady state response right here, and it goes in here. And the transient response is what we've been doing all along, which is these three different forms of the solution to the differential equation that depend on whether your roots of the characteristic equation, it's called because it's characteristic of how the circuit behaves, depends on whether the roots are real or whether part of the root goes away, so you get critically damped, or you get the underdamped situation when the roots are complex numbers. So this is the transient response. So we can therefore see that the final solution for the voltage in this circuit, with the application of a step to it, meaning the switch is closed and a voltage is applied, will be this. So here the solution is now completely defined except for the unknown coefficients A1 and A2, which we're going to use the same application of initial conditions to the circuit to find A1 and A2. So maybe this is all best shown by example. So we will do this example, at least part of this example, because gets a little repetitive to do all three cases, but maybe in one case I should. So we have this circuit right here, and you want to find the voltage in the capacitor. Remember, that's voltage in the capacitor here, and I in the inductor, defined in this direction, for t greater than 0. And we're going to consider three different cases, so you can probably guess one is underdamped, critically damped, and one of them will be overdamped. That's probably over, that one's probably under, and that one's probably critical, because that's the order your textbook does it in. So let's look at the circuit and what happens. So the first thing you have to do is look at what happens before. So it says the switch is opened at time t equals 0. So before the switch is opened, what does the circuit look like? So for t less than 0, we have an R. We know that the inductor is a short at that point in time, and when this switch is been closed for a long time, then anything that's charging the capacitor is fully charged up, so the capacitor will be an open circuit at that point, and so you're just left with this resistor in the circuit. So for case 1, case A, whatever, we have 5 ohms and we have 1 ohms. It's 24 volts, and so you get I, which is in the inductor, at time 0 is 24 volts divided by 5 plus 1 ohms, and so that will be 4 amps. That's one of our initial conditions. The other initial condition that we may need is the voltage across this capacitor, V0, so or before this switch is opened. So that would be the voltage between here and here. So that's pretty easy to get. It's going to be the I we've just found, I times R. So it's 4 amps times 1 ohm, which equals 4 volts. So we have those initial conditions, but now for t greater than 0, the switch is opened, which means if this switch is opened, this 1 ohm resistor is no longer in the circuit. So this part is disconnected from the circuit, and what we have left then is a series RLC circuit that we can analyze. So at t greater than 0, strangely enough, we still have this 24 volts in here, and we have this R, and we have this inductor, and we have this capacitor. The capacitor has an initial voltage on it of 4 volts. The inductor has an initial current here of 4 amps, and we still have 24 volts, and it's a series circuit. So the way you treat it with the series circuit being present is that you have to find the transient response, which is what we've been doing all along, and then the steady state response. So the final V of t for this circuit is going to be the V transient response, which is what we've been doing all along with the source being absent, plus the steady state response, which is going to be what the response is at t equals infinity. So to get the transient source, you have to get rid of the source. There's no source in the circuit, which means that you short it out. So I'm just going to short the circuit out, and at that point I clearly just have a series RLC circuit with initial conditions on it, 4 amps and 4 volts. So I go through my calculations from the RLC values. Alpha is R over 2L, which you calculate that and you'll get 2.5. And omega naught, the natural frequency, which has to do with the characteristic equation and how the circuit behaves in the absence of a source, is 1 over LC, and you compute that number and you'll get 2. And then I'll find my 2 roots, S1 and S2. They will be minus alpha plus or minus square root of alpha squared minus omega naught squared, and you'll end up with 2 roots, minus 1 and minus 4. So since alpha is greater than omega naught, we have the case of an overdamped. It's overdamped because alpha is greater than omega naught, and so we know that the solution will be of this form. V of t will equal V steady state plus A1 e to the S1 t plus A2 e to the S2 t. That will be the solution. We have our S1, we have our S2, we don't have our A's yet, and we don't have our V steady state yet. So we can get our A1s and A2s from the initial conditions once again. So we found these initial conditions right here. We don't have the derivative of the initial conditions, but we can get that here in a moment. So V at 0 equals 4, which we found, which equals this equation at t equals 0. So it's V steady state plus A1 e to the minus t plus A2 e to the minus 4t. And so you look at this circuit, and in the steady state, this source is back in here, and a long time, infinity time has gone by, and this capacitor is fully charged up. So what is V at the time equals infinity? It's 24 volts, because this capacitor will now be fully charged up to the 24 volts. So 4 equals 24 plus A1 plus A2, because it's at time equals, at t equals 0. So a moment of confusion there is that it is at t equals 0, because I thought, oh, you know, that's V steady state at t equals infinity, which would make this term go away. But that's not true, because we know that the solution that we're looking for is the transient plus the steady state. And so we have to find the steady state, and we know it's 24 volts, and we know the solution will have this form where the steady state response is part of the solution together with the transient response, and that will describe the whole solution. And it actually turns out that if you put t equals infinity into the equation, you will get that V equals 24 volts, right? So anyway, so that's one equation that we have, that minus 20 equals A1 plus A2. So that's one of our equations to get our initial conditions. So find our two coefficients A1 and A2. The other one that we need is that I at 0 equals C dV at 0 dt. That's our other initial condition, and we know that that equals 4 amps, and therefore, dot 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 means therefore dV dt at time equals 0 equals I at time equals 0 divided by C, which equals 4 divided by 0.25, which equals 16 volts per second. So now we have our two equations and two unknowns. The one equation was minus 20 equals A1 plus A2, and the other equation that we got was dV at 0 dt equals 16, which equals, and now we have to go back to the differential equation that we had, that the voltage as a function of time is 24 plus, plus A1 e to the minus t plus A2 e to the minus 4t, and then we have to find dV dt at time equals 0. So the derivative of that, and we know that that equals 16. So the derivative of this is 0, and we get minus A1 minus 4A2, and it equals 16. So we now have two equations and two unknowns right here and right here. And we go ahead and we solve for A1 and A2, and we get A1 is minus 64 thirds. Use your calculator. It's a 2 by 2 matrix. A2 equals 4 thirds, and we get the final solution, complete solution, which equals the steady state plus the transient, and we get the complete solution, which you can plot. So that's the complete solution that describes the voltage across the capacitor as a function of time. So maybe we also want to know what the current is doing in that circuit. So that's easy enough to get. The I, which is I in the inductor, but it's I everywhere because this is a series circuit. I is a function of time equals C dV dt. We have dV dt, so or we have V sub C, so all we have to do is take the derivative of that, and then and multiply by this factor of C, which in this case C was 0.25 farads. And so then you can also find out the current in the circuit. This is in amps, this is in volts. So we should note here that if we make the current be 0, or we make time be 0, that I will equal 4 amps as we expect. So now we have, for this equation, 2 more conditions. Whoops, sorry. So we'll go ahead and do the 2 more conditions. Well, I mean the 3 different cases, not conditions. So case 2, which I'm going to guess is going to be the critically damped condition. They've changed the value of the resistor in the circuit, and so the first thing we have to do is see what the circuit's doing before t equals 0 and get our initial conditions once again. So this is what the circuit is doing before the switch that is right here is opened. Switch has been closed for a long time. This is our initial circuit, same as the last one, except the resistor value is now different. So our initial current value is different. It's 24 volts divided by 4 plus 1 ohms. And then our initial voltage across the capacitor is also a different value because our current is a different value. So the next step would be to find alpha, just by calculating with the R and L values. But the other step that should have been done also was to find omega naught, and when you do that you will actually find that it is 2 also. So alpha naught equals omega naught, and we have the critically damped situation. So if you have the critically damped situation, we know the equation is going to be this form right here, or the solution. The equation of the solution to the second order differential equation is going to be this equation, have this form right here, and that S1 will equal S2 by virtue of these 2 values being the same. We still have to find the steady state conditions of the circuit. The steady state conditions are the same as before. This is when the switch is opened over here, and so this resistor is no longer in the circuit, and infinity time goes by, and the capacitor that was sitting here gets fully charged up. So the steady state voltage on the capacitor after a long time is 24 volts. So now we have almost the whole complete solution for what the voltage is across the capacitor in this series RLC circuit second order differential equation. All it's left to find now is the values of the coefficients A1 and A2, which we use our initial conditions for. So we have that the voltage across the capacitor at time 0 was 4.8 volts. We just found that, and so we put t equals 0 into this equation right here, and we know that it's 4.8 volts, so 4.8 volts equals 24 plus A1 plus A2 t. T is 0, so A2 goes away, and then e to the minus 2 times 0 is 1, and we get 4.8 equals 24 plus A1, and so that's nice. We get the value of A1 pretty easily, 19.2, and it's actually volts, because we have a solution here that's in volts, right? So that's A1. For A2, we use the other initial condition we have, which is I of 0 at 0 equals C dV at 0 dt, because remember, we need a V at 0 and we need a dV at 0, and we have this relationship right here, which makes it nice and easy for us because the I in the capacitor is the same as the I everywhere. So dV at 0 dt equals 1 over C I at 0, which was 4.8 amps, and so yes, so we get then that value there. Sorry, and I need to calculate it real quick. Oh, I messed up. No, that's a derivative formula. Whoops, I got a little mistake there. Let me get rid of that. Yes, I messed up. It's the derivative that we need. I do it too. So no, that's correct. We need to find that value. That because then we have to find a derivative next and plug that value in. So we have that. I calculated 1 over c. I forgot what c was. I think it's a, looking back here for a second. Oh, it's a quarter of a farad. So we have 4.8 divided by c, which will equal 19.2. So now we have that, but we have to find, we have dv of 0 dt is 19.2. So we go back and we take this equation right here, and we find the derivative of it. So ddt of v of t, which we have that value, is 19.2. And then take the derivative of this. So take the derivative of constant is still a constant. Take the derivative of this part will be minus 2a1 plus, and then we have to do the derivative inside there. Well, first we do the derivative here, a2t e to the minus 2t, and then actually it's easier if you, instead of doing it this way, that you split it up. So then you have to take the derivative of this part in here. So in the end you get minus 2a1 minus 2ta2, 2ta2 plus a2, which is the derivative of this part in here, and it's e to the minus 2t. And so then this is at time of 0, so you put the 0 in that you need, and you get 19.2 equals minus 2a1 plus a2. I now have two equations. Well, I have what a1 is. I have the second equation right here, so I can find out what a2 is. So that's what I do, and I get that a2 has the same value. Is that true? No, it's not. Yes, it is, because this one's 19, and you put minus 19.2 in for a1 right here, and it will come out. And so a1 and a2 actually are both the value of, you get between these two equations and two unknowns, you get that a1 is minus 19.2, and you'll get that a2 is also minus 19.2, and then you put all of those numbers back in here, the a1, the a2, you got the root right there, you got the 24, and you get the full solution to this, the full solution that describes the voltage across the capacitor for all time, or for time greater than 0, I should say. And then if you want the current in the loop, you take the derivative of this, and you can get the current in the loop as well. So the third case, they changed the resistor value one more time. The third case is probably going to be the underdamped case, but let's go through it. So now the resistor, well, the circuit looks like this at t equals 0 minus. We now have a 1 ohm resistor there. The capacitor is open right now, and we have another 1 ohm resistor right here. And so we have to find the initial conditions. So we find the initial conditions is now 24 volts divided by 2 ohms. We get 12 amps. And the voltage then that's at between these terminals where the capacitor is sitting here being open is now I times R, which is, there's I, so there's R, so it's 12 volts. So the next step in the process, always over and over again, is find alpha. So alpha is R over 2L. We compute it, and then there's that number. The next thing, which somehow your book left out, was to find the omega naught. And when we do that, we will actually find out that this value will equal 2. So omega naught is bigger than alpha. That means that we are going to have the underdamped case, and our roots are going to be complex. Because when we calculate this formula right here for the two roots, S1 and S2, roots of the characteristic equation, then we get this value, and this is complex number. So there's our two roots, and then you can put it into the total response of the circuit right here just by using these values that we calculated. So you'll get the same V steady state right here, plus the V transient part is right here, taking into account that our roots are complex. So you put the imaginary part here in the sine and cosine, and the whole thing is multiplied by this decay portion of it. This is the part actually should have talked about it more. It's going to have a response that's oscillatory. How much it oscillates, I don't know. But this decay, this envelope here, is driven by this part right here. This causes the decay envelope right there. So that's actually e to the minus 0.5 t multiplied times this sinusoidal-ish function right here. So it causes the amplitude to decrease. Okay, so all that's left now to find is the unknown coefficients a1 and a2, and no surprise by this time, I hope, that you're going to find it kind of in a similar fashion. So we have to determine a1 and a2. So we first look at voltage at time 0, which is across the capacitor. We said was 12 volts, and that equals that equation that we just had a moment ago, evaluated at t equals 0. So it was 24 plus a1. So this is going to be cosine 1.936 t, but t is 0, so cosine of 0 is a 1, plus a2, and this is a sine function here, sine of something t, but sine of 0 is 0, right? And then we have the e to the minus 2 evaluated at time t. So we get 12 equals 24 plus a1. So a1 equals minus 12. So that's one application of initial conditions. The other application of initial conditions that we need is we need dV at 0 dt, so that we can find our other unknown coefficient a2. And we find this because we know that c dV dt equals I sub c, or the current at time 0, and which we found. We found that the current at time 0 was 12, so therefore dV at 0 dt equals 12 divided by 12 amps divided by C. And C, value of C, oh, it was a quarter farad, right? Wasn't it a quarter? Yes, it was a 1/4 farad. So it's 48 amps per farad right there. So now we take our assumed solution and we find a derivative of it and set it equal to 48. So dV at 0 dt equals 48, which equals, well, derivative of the derivative of a constant is 0 plus, and now we have to find a derivative of these two terms. So I actually prefer to break it up, but it's e to the minus 2t a1 cosine 1.936 t plus e to the minus 2t a2 sine 1.936 t, and we need to find a derivative of that, d dt of this total amount right here. So doing these two derivatives right here, we did it, I think, early on in chapter 1 or chapter 2. To me, rather than reapplying the derivative formulas, it's easier just to look them up. So you do the derivatives for these two portions right here, and then you set t equal to 0. And when you do that, you don't need to watch me do the math. You should look up the math for yourself if you're rusty on it. rather than using a bunch of YouTube time to do the math because we did it earlier in the semester. So you'll get minus 0 plus 1.936 A2 minus 0.5 A1 plus 0. You can work through that math, but in the end, we already had A1 right here, so then you solve for A2, and A2 will be 21.694. So then you go back and you reconstruct the final complete solution, which is this. Oh, sine. I almost want to not write it. Okay, sine 1.936t minus 12 cosine 1.936t and e to the minus 2t. So that's the complete solution. And of course, if you want to find the current in the inductor, you can take the derivative of this to get the current in the inductor from the relationship that I equals C dV dt. One current anywhere, so that gives you the current in the inductor. So it is kind of nice to look at the response, the 3 different responses for this circuit, and I could put it in MATLAB and program it out for you, but whoops, new slide. I could do that, but I don't need to do that, but you can see the total responses in your textbook, and I'll just repeat it here because it's informative. Whoops, here it is. Shrink it down a little bit. So underdamped has the oscillatory behavior, and that's time on the horizontal axis. But the underdamped has kind of an envelope of decay right here, which I was talking about a moment ago. This decay envelope is the e to the minus 2t part of the underdamped equation. Critically damped and overdamped never look significantly different, but they always had the same kind of shape. But we differentiate critically damped because the moment you get past critically damped and into the underdamped, the oscillatory behavior will begin, and there will be a slight overshoot and a slight oscillation, which the more underdamped it is, the bigger this oscillation will be. So the step response for a parallel RLC circuit is going to follow the same development as we did for the series RLC circuit, except once again in a parallel circuit we're concerned with a solution that's in the form of a current. So this part I thought was a little bit confusing the way it was shown in the textbook, is that we're giving a solution of for current, but yet when we deal with a parallel circuit we end up with a differential equation that's a function of voltage, or whose solution is a voltage equation. It's a differential equation in V. So let me just go back and see. I should have done it on the other circuit, but I can do it in this and you'll see that the same thing occurs. So remember, for this parallel circuit we are doing a KCL, and an IR plus an IL plus an IC, and it's going to equal an IS in our forced solution. So that's a VR over R, which is the same V everywhere, plus 1 over L integral of V plus and I sub C we have is C dV dt equals IS. So this looks like, I mean, we're doing KCL and these are currents that we're adding together, but it looks like the solution is a voltage function, which yes it is. So we want to see a current function because one, we know what I steady state is in this case because we're applying a current step. So we would really like to see it be a current solution, and I should have done this with the series case, but it's actually a pretty easy substitution to put in and you can see what happens. So what you end up doing is that you recognize from this equation that V equals L di dt, and I substitute it back up into our original KCL equation. So I substitute L di dt for V here, and so integral of the derivative is just going to be the I, and derivative twice will occur here. And then when I do that, I get d squared I dt squared, and rearranging the terms, 1 over RC di dt plus I over LC equals IS over LC. And so the point of doing this right now is that if you look at the coefficients and you determine what the roots S1 and S2 are, S1 and S2 will be the same roots as this equation, or this equation up here that was in voltage. So the natural response is still the same. But since we're going to do an equation for current, the natural response is still the same. We'll find coefficients that are appropriate in terms of current, and then we'll use the steady state response in the final solution. So that's how you translate between seeing this mixed I and V and getting it into an equation of I, and then recognize that the roots of this equation, S1 and S2, are the same as the roots of this equation when it was all in V. So this is what we just did by our substitution, and this was the equation that we got for the parallel circuit natural response, source-free. So it was an equation in V. It came out like this, but if you see that the coefficients here are exactly the same as the coefficients of this equation down here, then we know that the roots S1 and S2 are the same. And the only thing that's different now is the steady state response and the coefficients A1 and A2. So, but the roots S1 and S2 are the same, so we do our same test of seeing whether the circuit is overdamped, critically damped, or underdamped, and then we apply our initial conditions and get the answers. So now let's summarize and generalize what we've just done for our circuits. So we had a series and a parallel circuit, and we found the transient response, and then and these are second order equations. And then we found the steady state response, and we could add it to find the complete solution. So we can apply that to other circuits that aren't just purely series or purely parallel by going through a series of steps and then developing a differential equation and then solving it with the means that we have learned to solve them with in this chapter and the last chapter. As you simplify a circuit, it may turn into a first order circuit instead of a second order circuit, in which case you'll go back to the solutions that you had in chapter 7 for a first order differential equation, which has an exponential response with only one exponent in the exponential. So generally, given any second order circuit right now, we can determine its step response, which may be a voltage or a current, by taking 4 basic steps. First, you have to determine the initial conditions in the circuit before the switch closes or the switch opens or whatever has to happen. So generically we'll say X, which may be current or voltage. And then you have to find the steady state, whatever the current or voltage is at infinity. So these are the things to keep in mind with step 1, is that on a capacitor, the voltage at 0 plus is the same at the voltage at 0 minus. So the capacitor voltage doesn't change instantaneously. And for the inductor, the inductor current cannot change instantaneously either, before and after 0 or whatever event occurs. So in this chapter, V's are V sub C's and I's are I sub L's, but since in a series circuit there's only one I, or in a parallel circuit there's only one V, you can use that to your advantage. The other initial conditions that you have to find the initial value of I or V, and then you have to find the derivative of I or V, and the I or V. These are the initial conditions that you need. So I is found from this relationship, which from which you can get that the derivative that you need is this equation. In a series circuit, that works. And the V, you can use this formula to get the initial conditions on di dt here, and in the parallel circuit. So the next step is you turn off all the independent sources, that's your voltage and current sources, and you find the transient response by applying KCL and KVL. And then sometimes you'll have two equations and two unknowns that you combine one differential equation with the other differential equation, which is the example I'm going to show you, and then you get one final differential equation in one of the variables, either I or V. So from that second order differential equation, you find its characteristic roots. And depending on whether that response is overdamped critically or underdamped, then you obtain a solution, a form of the solution with two unknown constants or coefficients. So from step 2, you'll find the roots of the differential equation, which is called the characteristic equation. You'll find the roots S1 and S2. The third step is to find the steady state response, so the value of the voltage or the current at x equals infinity. And always remember when you're doing that capacitors are open circuits after infinity time has gone by, and inductors are short circuits after infinity time has gone by. And that helps you find the simplified circuit and whatever the steady state response is. And then you find the total response by adding the transient response plus the steady state response. Then lastly, you find your unknown constants that are associated with the transient response by imposing the initial conditions that you determined in step 1. So I said these problems are kind of difficult to do, and that we'll find an easier way. So we'll learn how to solve these problems using Laplace transforms, which are covered in chapter 15 and 16. And it's actually much easier to solve these problems that way. For now, you should really just practice these problems. These are not easy problems to just look at and know how to do. It comes with time and practice on these problems. So let's do an example. It's out of your textbook, but it shows pulling together all of our knowledge and all of our tools together to solve the problem. So I like this problem actually. So let's follow our steps. I'll get rid of that streak I just made. Let's follow the steps that we were given for generically how to solve the problem. So step 1 was to find the initial conditions in the circuit. So we should do that by applying the rules that we already know. So it says that for t less than 0, this switch is open here. If this switch is open right here, this part of the circuit does not exist in the circuit. So the 2 ohm resistor is not in play. And we've gone from time minus infinity to 0 minus. So the capacitor is fully charged up. It's charged up to this voltage here, and current is no longer flowing in the circuit. And we only have this outside loop to consider since the middle part is not there. And so that means that the voltage, and it's the voltage on the capacitor at 0 minus, which equals the voltage on the capacitor at time 0 plus, equals 12 volts because it's fully charged. Since it's fully charged, no current can flow, which means that there's no current flowing in this loop. We also know that this inductor is a short right now, but it doesn't matter because now there's no longer current flowing in the loop. So we have I at time 0 minus equals I at time 0 plus, and it's this I right here, which is really I in the inductor, which equals 0 because right now that loop is open right now, and so we can't have any current flowing. So the next thing you have to do is find the derivative, at least one of the derivatives. Whether we do a current or voltage equation yet, we're not quite sure, but we have to find some derivative initial conditions. You can, by practicing, I can see that we could get dV dt at time 0 plus from the equation c dv dt equals I sub c. And at time 0 plus, what happens? At time 0 plus, the switch has closed, so this resistor is in the circuit, so we have current in this leg, a rate of change of current in this leg, and a rate of change of current in this leg, and a rate of change of current in the entire circuit. Even though initially this current was initially 0, this part of the switch has closed, and this capacitor is going to start discharging, likely, some of its charge within this loop right here. But we need to find out. So I'm not clearly series, I'm not clearly parallel, so I'm going to apply KCL to determine these derivative, either I or V's that we need. So I'm going to apply KCL to this loop at node A, on the circuit at node A. And so I can say I equals I in the R, where this is the R, I in the 2 ohms, plus I in the capacitor, correct? So we do have that I at 0 plus was 0. And then we have I in the resistor. Well, at time 0 plus we have 12 volts across here. So it's 12 volts divided by 2 ohms. And plus I in the capacitor, which is C dV dt. So that's what I in the capacitor is at time 0 plus. So we can solve for that, and then we'll get dV at 0 plus dt equals minus 6 over 0.5 is the capacitor, and it equals minus 12 volts per second. So we have at least one of the derivatives that we need, which would be sufficient if we have an equation and V, and that will be sufficient for us to find our unknown coefficients A1 and A2. The other thing that we might consider looking at this point in time is what either I or V looks like at t equals infinity. So I at t equals infinity is, so at infinity, this thing has been closed for an infinite amount of time now. If it's been closed for an infinite amount of time, this capacitor is now fully charged up to whatever it's going to charge up to be, so no current will be flowing in this leg. And we have this, only this loop to consider, and this inductor at time infinity is a short, so the current now, I at infinity, is 12 volts divided by 4 plus 2 ohms, which equals 2 amps. And now we can actually find V at infinity also, because we have the I that's going through this leg right here, so it must be I times R, which is 2 amps times 2 ohms, which equals 4 volts. So now we've completed step 1. We have all our initial conditions, and then we also have our final steady state condition that will come into play with whichever equation we want to do. So now it's time to find a transient response for this circuit. That would be step 2. So the switch is now closed, and we need to find a transient response. So transient response means that the source is not present in here. So this is closed, or this is shorted out, because the for transient response you either short out the voltage source or open up the current source. So that means that at this point in time I still have, with this being a short, I have these two components in there. This component is in there, and this component is in there. So that it's not a pure series and it's not a pure parallel, and I'm going to have to apply KCL or KVL. So I'm going to apply KCL at that node again. And so I get I, just like I did before, is this I equals this I plus this I in the resistor plus I in the capacitor. But now I'm not doing putting the initial conditions in it. So I, which is in the inductor, equals V over R, or V over the 2 ohms, plus C dV dt, which equals V over 2 plus 1/2 dV dt. Okay, so I still have, I have an I have a V, I have a dV dt. I still don't have a pure equation in either I or V, which I need to get my second order differential equation. So now I'm going to do KCL around this loop. I'll do KCL here. I mean KVL, sorry, KVL. This is not present in there, but if I just apply KVL around the loop, I have loop, left loop. Let's say KVL at the left loop. It's I times 4 ohms is that voltage drop, right? Plus L di dt right here, and L is 1 Henry, so it's 1 di dt, plus this voltage here, V, equals 0. So I have, actually now, I have a differential equation in V and I here, or an equation in I. It's a differential equation for I, and I have a differential equation right here. I have I's and V's floating around all over the place. I'm going to take this I right here and substitute it into this equation. So now I have V over 2 plus 1/2 dV dt times 4 plus 1 di dt. So I need a ddt of this equation right here, of V over R plus C dV dt. So I need to differentiate that. Oops, sorry. Yes, that's correct, which is this right here. Yeah. So, and plus V, that's this term right here, plus V equals 0. And so we can do this, not a problem, and we will get d squared V dt squared plus 5 dV dt plus 6V equals 0. From this we can substitute our assumed solution a e to the st into this equation right here, and we will get our characteristic equation, which will be s squared plus 5s plus 6 equals 0. So this characteristic equation, even without knowing RLC values, we can just apply our quadratic formula and we'll get that S1 equals -2 and S2 equals -3. So we find our two roots, and so we can write the natural response. This is an equation in V, so we can write the natural response, which is also the transient response, is a e to the -2t plus, or a1, a2, but I'm going to say ab this time because your textbook did. So I've got two roots here, and they were not equal roots. So either, if they were equal roots, we would know that it is a critically damped solution. If they're unequal roots but real, we know that it's an underdamped situation. And if they were two roots that were complex roots, that you would know that we had a underdamped solution. So the A and B, or the A1, B1s, or A1, A2s as the textbook previously called, are to be determined from the initial conditions. When we also got our steady state answer, where's our steady state? I know we had a steady state. It was on the previous slide. So our steady state voltage at infinity was 4 volts. So we get the final form of the solution, which would be the steady state plus a e to the minus 2t plus b e to the minus 3t. All that's left now is for us to find the values of a and b, and we'll do that by applying our initial conditions. So I wrote all the things that we have found, all the initial conditions and final conditions that we have found so far at the top of this slide, so because it's hard to, you don't have a whole board to look at right now. And then the complete response repeated from the previous slide is right here. So we want to find the unknown coefficients or constants a and b. So v at 0, which was 12, equals 4 plus a e to the 0 plus b e to the 0. So we get a plus b equals 8. Then we have to find dv dt. So we take the derivative of this. So this is a 0, and we get minus 2a e to the minus 2t plus minus 3b e to the minus 2t. And that equals minus 12. And t equals 0, so we get minus 12 equals minus 2a plus minus 3b. So now I have two equations and two unknowns. I solve for a and b, and I get that a equals 12 and b equals minus 4. And so now I can make the entire complete solution. V of t equals 4 plus 12 e to the minus 2t plus minus 4 e to the minus 3t. And I can get I of t if I want. I of t, because I of t equals c dv dt. And so multiply times c and take the derivative of this, and you get the I of t. You can obtain the other quantities of interest in this, like we had written an equation for a KCL equation here. So we had an I, we have a v over r here, we have an I here that's c dv dt. So you can go through and get the other quantities of interest in this circuit too. Maybe we should do this I right here. This I is actually I in the capacitor, because it's related to this equation V, which was V in the capacitor that we determined. If we wanted to find this I in the inductor, remember we had two equations and two unknowns, and so we have to say I in the inductor was V, this is always V right here, V over to that equation that we had at the KCL written for that node, dV dt, and then we can find I in the inductor. So this would be I in the capacitor if we just took the derivative of that and multiplied it by C, and this would be I that's I in the inductor, by definition of the fact that we had to do two equations and two unknowns, and they were differential equations. So